Knowing the rank nullity theorem will let us analyze a special kind of matrix with surprising effectiveness. So just a reminder, the rank nullity theorem says that for any matrix, the rank of the matrix plus the nullity of the matrix equals the number of columns of the matrix. Remember, when we interpret this in terms of linear vector functions, a matrix is a linear vector function from Rn to Rm, and it acts by taking a vector and multiplying on the left by A. Okay, so the special kind of matrix I'm talking about are called matrices of full rank. So a matrix is said to be of full rank if the rank of the matrix is as large as possible. Well, how large is as large as possible? Remember that the rank of a matrix is the number of pivots in the reduced row echelon form of that matrix, but you can only have as many pivots as rows, but also only as many as columns, and that means that the rank of a matrix can't be any bigger than the minimum of the number of rows or the number of columns, and that means that the maximum rank is the minimum of those two, the number of rows and the number of columns. What we'll see is the matrices of full rank, they have their own geometry, but what that geometry means, or what it is, and sort of the consequences of being a full rank, really depends on whether the rank is full because it's equal to m, or whether it's full because it's equal to n. But before we look into the consequences of being a full rank, let's interpret what the geometry of full rank is. So first, let's suppose that the rank of our matrix is m. All right. Well, remember the rank, one interpretation we have for the rank is that it's the dimension of the row space, but one thing we know is that the dimension of the row space and the dimension of the column space are equal. And the dimension of the column space, we called that the image. So this is the dimension of the image. Okay, so this matrix A is a linear vector function from Rn to Rm, and in this situation, our matrix has rank m, but that means that it fills up the target space, which sometimes is called the codomain. Okay, so being of full rank because your rank is the number of rows, that means that you fill up your target space. Okay, so that means that every vector in the target space is hit by some vector coming from Rn. The other possible way of being of full rank is that your rank is actually equal to the number of columns in the matrix, so that's n. And what would that mean? Well, one thing we know about rank is the rank nullity theorem, which says that the rank of A plus the nullity of A is equal to n. But if you're of full rank because your rank is equal to n, then we have something like this. That means, n over here. That means that your nullity has to be 0 in this case. So if you're of full rank because your rank is n, that means your nullity is 0. And what does that look like? Well, in that case, A is a linear vector function from Rn to Rm. That means that whatever Euclidean space you're starting in, so Rm, I guess I'll draw as if it's three-dimensional, the nullity is 0. But that means that, remember, the nullity is sort of a measure of how many dimensions the linear vector function sort of squashes down to nothing. So if your nullity is 0, that means this linear vector function doesn't squash any dimensions down to 0. And so really it's just taking this space that we're starting with and sort of situating it somehow in your target space. So if you're a full rank because your rank is equal to n, that means that in your target space there's a perfect copy of the space that you came from because none of it gets squashed down.